about this interesting project, and I think I'll just let you roll. And you can deal with questions or comments however you like. If you want to tell people to be quiet till the end, or some of the burning questions.
If someone has a burning question, ask me. Otherwise, I'm happy to take questions at the end. So, I'm Jessy Rivest. This is my PhD exit seminar, and I'm going to be telling you over the next 40 minutes about the research I've done for the last 4 years surrounding nanocrystal photovoltaics, and specifically the chemistry of copper sulfide, cadmium sulfide. So along the way, you'll see this progress bar. So you know, talk isn't going to go on forever. I've done 3 projects in my PhD. Self-assembly, heterojunctions, and then size effects. But before I get into the technical portion of my talk, I want to make sure I hit the most important slide. My dissertation committee consists of David Dornfeld, Paula Levisatos in the chemistry department, Alice Agagino, and Peidong Yang, also in the chemistry department. And these people have guided my research, my teaching assistantships, and also given me a lot of career advice. Additionally, Arun Majumdar, Rachel Siegelman, and Dan Cameron have helped me look deeper into my experimental results and have helped to brainstorm how to have stronger applicability to the field of energy. Jesse Engels, Sebastian Lunas, and I co-taught a graduate-level photovoltaics course this past spring in the Materials Science and Engineering Division. And I've been lucky to have a large handful of collaborators who have enriched both the papers we've written together and the entire scientific process along the way. Lam Q. Fong, Sarah Swisher, Asa Woodmer-Cooper, Phil Geisler, Bryce Sattler, Prashant Jain, Delia Miller, Jeff Urban, Jaime Zhang, and Mike Tony. My lab mates in the Oliver Santos lab, Trevor Ewers, Karina Choi, Lilac Amarov, Matt Lucas, Mingli Tang, and Jessica Smith have all been extremely supportive, and they've been there to empathize when I have no idea what to do next or when I'm jumping for joy about my results. They've also taught me everything I know about chemistry. And finally, my friends and family, Libby Wayman, my sister, Nikki Baker, my mother, Kitty Baker, and my husband, Chris Rivest. So I've also been lucky to have fellowships from both NSF and later from Intel so I could focus on my research rather than fundraising. And without this group of people, the process of my PhD would not have been nearly as fun or as productive. So thank you all. So I came to Berkeley after a short stint in industry at a company called Evergreen Solar, which makes silicon solar cells. And when I got here, I really wanted to do research that would contribute to low-cost and high-efficiency photovoltaics devices. So I outlined a few design requirements that I wanted to work toward. First, I wanted to make sure that whatever device I made was made of abundant materials. If we were going to get these devices to be economical and also to reach scale, 13 terawatts, we didn't want to have any material constraints. Next, I wanted to make sure these devices were solution processable. I wanted to make sure that we wouldn't need any fancy processing equipment that would increase the cost of them. Third, I wanted to make sure they had high through-film carrier mobility, which would enable them to have a high efficiency. And I wanted the chemistry to have shown potential for an efficiency of at least 10%. 10% is often cited as the magic number of efficiency, below which it doesn't make sense to make solar cells due to the cost of what's called the balance of systems, so the racking, the mounting, and the power electronics that support the photovoltaics. So in order to get to high efficiency, industry usually tries to improve crystallinity and work toward a single crystal device. But in fact, in a solar cell, we have a top contact and a bottom contact, or electrodes. And between those two electrodes, electrons need to move perpendicular to the film. It's not really important that they be able to move easily in plane. So when industry is working toward a single crystal, we're enabling the electrons to move easily in all directions. But in fact, we only need this perpendicular direction. So who cares? Why don't we just go with the single crystals? Well, single crystals are very difficult to grow in large scale, and they're very energy intensive and expensive. So as a practical example, if you've ever been shopping for a diamond, you know that when you double the size of the diamond, you do a lot more than double the price of the diamond. And that's because it's so difficult to get a large single crystal. But on the other end of the spectrum, diamond tips are used in cutting tools, and they were used in record players, so they're really cheap. So I wondered if we could use nanocrystals to meet all of these design requirements. So for those of you not familiar with nanoparticles, or nanocrystals, a nanocrystal is a very small crystal whose dimensions are on the order of nanometers, or 10 to the 9 meters. They consist of an inorganic core that's coated by organic molecules called ligands. And these serve to passivate all the bonds on the surface of the crystal and also to solubilize them in some solvent. This gives you a nanocrystalline ink that you can then process very easily. And so one very easy example to show of what's interesting about nanocrystals and their size tunability is that in this image, all of these nanocrystal inks have the same composition. They're all indium phosphide. And the reason they're different colors is because of their size. So nanocrystals have these size tunable properties, not just color, optical properties, electrical, thermal, and strength properties that are all dependent upon the size and shape of the nanocrystal. So these are transmission electron microscope images of spherically shaped nanocrystals, but we can make a variety of other shapes, including rod-shaped nanocrystals. This bottom image is a transmission electron microscope image of a single nanorod. And the stripes that you see are actually rows of atoms. And you can see that these rows are very orderly and occur in a single domain. So this is a single crystalline nanorod. So what if we could take a nanocrystal ink made of nanorods, and we could induce all of those nanorods to stand perpendicular to the substrate? Then we would have good carrier mobility. The electrons could move easily between the electrodes, but we wouldn't have wasted all the effort on having good crystallinity in plane of the film because it doesn't help the performance of our device. Well, if we could do that, then we'd be pretty far along in our design requirements, because you can make nanocrystals out of a wide variety of materials. We chose our starting material to be cadmium sulfide, which is earth abundant. They're certainly solution processable. Nanocrystal inks can be printed, sprayed, or painted onto any substrate. And so our next step was to hit this through carrier film mobility requirement. So we needed to work on this geometry. After that, we're going to need to make it look like a solar cell by inducing some sort of asymmetry in the film. But first we'll talk about how to get this geometrical arrangement. We set about studying self-assembly with the objective of getting nanorods to stand up on a large area. And for nanocrystals, a large area isn't that large. But we thought a square centimeter would demonstrate the applicability of this and the scalability of this type of method. And so this would give us effectively a single crystal solution processed semiconductor thin film. So I'll cut straight to the punchline and tell you we were able to do this. These are electron microscope images, and you're looking down on the forest of aligned nanorods. So each of these dots is one nanorod standing up. So in order to do this, we didn't apply electric fields or magnetic fields, and we didn't use any form of mechanical manipulation. So why would the nanorods want to stand like this? It must be some combination of dynamics and thermodynamics. So let's think about the thermodynamics of this. It might be surprising that entropy could help bring order to a system, but in fact entropy can help us in two ways to align these nanorods. The first one was outlined by Lars Ansager in 1949 and is known as the Ansager hard rod model. When he was thinking about this in 1949, he wasn't thinking of nanocrystals in particular, but he was thinking of any model system with long and undeformable rods that were tumbling freely in some contained volume. And this is analogous to our nanorod case, where the containing volume is the solvent. The nanorods aren't going to jump out of the solvent. So when these rods are tumbling freely, they have translational freedom and they have rotational freedom. And the rotational freedom carves out an excluded volume, which is a sphere whose diameter is equal to the length of the nanorod. When we start to evaporate the solvent, or when we start to shrink that containing volume, our excluded volumes begin to overlap. And at that point, the rods start to hit each other, and it's actually a net gain in entropy if they give up some of their rotational freedom in exchange for more translational freedom. So this accounts for the liquid crystal pneumatic phase transition, where all the rods point roughly in the same direction. So now we continue evaporating the solvent, and the rods get packed together until there is no more solvent and the rods are a nice assembly. The next way entropy brings order to a system is known as depletion attraction. It was outlined theoretically in 1997 by Volhuis and demonstrated experimentally just last year by Baranov et al. Depletion attraction requires the addition of a depleting agent to a system, which is not something that we're doing purposefully, but recall that our nanorods are coated with these organic ligands. And the ligands have some mobility, so they're popping on and off in a dynamic equilibrium. And when they're off the rod, they could very well be acting as depleting agents. So the way that you can think about depletion attraction is also to use exclusion